Hello class, welcome to this level 6 embedded system design. My name is Juan Pablo Martinez Brito. In this lecture, we will compare two ways of receiving UART data on the STM32, interrupt-driven reception versus the DMA-driven reception. So the goal is to understand not just how they work, but when each one should be used. So let's move on. So this is today's lecture overview. We will start with a quick STM32 architecture recap, then look at the interrupt-based UART reception, followed by the DMA-based reception. After that, I will explain normal versus circular DMA modes, and we will finish with a register level comparison and a practical example. This figure shows a conceptual view of the STM internal architecture. At the center, we have the Cortex M4 core, which executes the application code and interrupt handlers. The CPU, memory, and peripherals are connected through a bus matrix, which allows multiple masters, such as the CPU and DMA controller, to access memories and peripherals. Program code is stored in the flash, while SRAM is used for runtime data, including UART receive buffers. Peripherals such as the USART interface with the external world and place receive data into internal registers. In this lecture, we focus on how data moves from the USART peripheral to the SRAM, either through CPU interrupts or using the DMA controller. So why UART reception matters? So when a microcontroller receives data via UART, it must continue running other tasks at the same time. Example, blinking LEDs, updating variables, or running control loops. If the CPU is forced to wait the UART to finish transferring every byte, then the CPU is blocked. Other tasks suffer delays and time-sensitive processes get distorted. So this is what happens in blocking mode, where the CPU is actively involved in every received byte. So to overcome this, we replace that with interrupts. So CPU is notified only when necessary, or we move to the DMA. Data is transferred occurs without, the data is transferred without the CPU involvement, freeing processing resources. This slide shows how interrupt-driven UART reception works. The UART hardware continuously monitors incoming data while the CPU runs the main application. First, the UART peripheral receives a byte from the serial line. The peripheral detects this event internally and flags that new data is available. This causes the CPU to be interrupted. The CPU then handles the received byte, typically by reading it and storing in the memory. After that, the CPU resumes the main task it was executing before. So let's see on the next slide how STM32 microcontrollers handle it. So this is how STM32 handles interrupt-driven UART reception. So let's go to the flowchart. So a byte is received via UART RX pin, and then this byte is stored on the USART that data register. After that, you have the RxNE flag equal 1, saying that data is waiting to be read. And then having this RxNE equal 1 and the RxNE YE equal 1, 2. These two bits are inside RxNE, it's inside the USART status register. And the other one, the RxNI interrupt enable, it's a control bit inside the USART control register 1. If both are 1, so an interrupt request is generated. That means that a signal sent from the USART to the NVIC, which requests an interrupt to the CPU. So the CPU is interrupted. Then the CPU reads the USART data register. Then this makes a copy, the CPU makes a copy of the received byte into the memory. When this process is finished, the RxNI flag is cleared, so equals 0. The CPU after that returns to the normal execution, and then the WART is now ready to receive new data. So every byte triggers an entire chain. The CPU is involved once per byte. The WART hardware does part of the work, but data movement from the USART data register to the memory, it's done by the CPU. So we have the pros and cons of interrupt-driven WART receptions. The cons is it's 1 interrupt per received byte. So CPU must handle every byte. Every byte it arrives, you need to interrupt the CPU. So interrupt overhead increases with data rate. So the pros, it's good for moderate data rates, lower latency than pooling, and you have a precise control over reception events. So interrupts are great for small or irregular data, but every byte requires a CPU intervention, which becomes costly for continuous streams. So let's move to the DMA approach that overcomes this issue. So how to overcome this CPU interruption every byte transferred? We use this technique called this DMA, direct memory access, which is the interaction directly with the memory. It's a control block that transfers data from the peripheral directly to the memory without any CPU intervention. So it allows that data to be transferred between memory and peripherals. It can be also between memory and memory, but in this example, it's just between memory and peripherals, like WART, without involving the CPU. When using DMA, the WART peripheral data transmission becomes faster and more efficient, especially during large and continuous data transfers. This helps keep the CPU free to perform other tasks, improving overall system performance. So in short, we can say that in the interrupt, the CPU handles every byte, and the DMA mode hardware handles the data, and then CPU handles the event. So let's see how the STM32 handle it. So let's first look at the configuration registers involved in the DMA-driven WART reception. The USART CR3DMAR enables DMA requests from the WART receiver. The DMA SX par defines the peripheral address, which is the WART data register. The DMA SRMOAR defines the start address of the memory buffer where the data will be stored. The DMA SX and DTR sets how many bytes will be transferred, and the DMA SX CR configures the DMA mode, such as normal or circular mode. Once these registers are configured, the DMA hardware takes over the data movement. So CPU is only interrupted when a half buffer is filled, is optional, or at the end when a full buffer is filled. So let's move on to the DMA modes. So DMA, we have 2 modes on the DMA. We have this normal mode, which DMA copies n bytes and then stops. So DMA interrupt fires once, saying transfer is complete. So this mode is good for one-shot data blocks. And then you have the option for circular mode, which is targeted for, let's say, real-time, for example, sensor or interface or audio-video acquisition. So after finishing the buffer, the DMA automatically restarts from the beginning. So the hardware continuously streams incoming data into the same buffer. We can use half transfer or full transfer flags in a combination to produce this. We can use like a double buffering. So double buffering means while a DMA is filling one half of the buffer, the CPU can simultaneously process the other half, allowing continuous data streaming without stopping transfer. So when you fulfill a half, you at the same time processing the other half. This is speed up the process. So here we have a comparison between the interrupt and DMA driven data handling at the register level. So we can ask who moves the byte. In interrupt mode, the CPU copies from the USART data register. On the DMA mode, the DMA engine copies automatically. So what is the NVIC load, the interruption controller load? In interruption mode, high if data rate is high. So it depends on the data rate. In the case of DMA mode, it's minimal. So the interrupt only occurs when the transfer is complete, so on block completion. The CPU involvement in every mode, so interrupt mode, it's per byte. DML mode is per buffer. So you don't bother every time you transfer a byte. So you bother the CPU when you transfer, when you complete a whole buffer. That's the advantage of DMA mode. The interrupt mode is best for small and irregular data. And DML mode, it's good for large and continuous streams. So these are the key registers involved. So conclusion of this lecture, we can say that interrupts shift work away from pooling, but using DMA shifts work away from interrupts. So DMA represents the highest efficiency path, no CPU stalls, no per byte overhead, and ideal for embedded systems where concurrency matters. So thank you very much. I hope you enjoyed the lecture. See you next time.